Hi, myself Dr. S.K. Bushra. This is a video lecture in physics for class 12 students. The topic is electrostatics. Lesson 2 of chapter 2 on electric potential part 2. In this lesson, we'll consider potential due to an electric dipole, equipotential surfaces, relation between electric field and potential, potential energy of a point charge distribution, and finally, potential energy of a dipole in a uniform electric field. So let's begin. The first topic, potential due to an electric dipole. Let us find the approximate potential at points far away from an electric dipole. Let the field point P be situated at a distance r minus from minus q and r plus from plus q. The other parameters have been illustrated in the figure. Then, from the principle of superposition, the potential at P is, as given by equation 1 by 4 pi epsilon naught within bracket q by r plus minus q by r minus. And from law of cosines, we get r plus minus square equal to, as given by equation 2. For a dipole of molecular size, r is too large with respect to d. We can therefore safely neglect the third term. Thus, equation 3 simplifies the expression for r plus minus square. Carrying out binomial expansion and retaining only the first two terms, the reason being the subsequent terms being very small, we get 1 by r plus minus as given by equation 4. Thus, if we express 1 by r plus minus 1 by r minus, we get finally 2d by r square into cos theta. This is equation 5. And hence, potential at P is finally given as 1 by 4 pi epsilon naught vector P dot r cap divided by r square. This is equation 6. Here, Q into 2D is equal to P, which is the dipole moment, and r cap is a unit vector along the vector r. The potential of a dipole goes like 1 by r square at large r. It falls off more rapidly than the potential of a point charge. Special case 1, when the field point is situated on the equatorial line of the dipole. In this case, theta equal to 90 degree, and so potential at P for theta equal to 90 degree is ultimately equal to 0, because cos theta will be replaced with cos 90, which is equal to 0. Special case 2, when the field point is situated on the axis of the dipole. In this case, theta is either equal to 0 degree, that is, the field point is situated to the left of the positive charge, or 180 degree, that is, the field point is situated to the right of the negative charge. Now, for theta equal to 0 degree, we have V at P equal to 1 by 4 pi epsilon naught P by r square. And for theta equal to 180 degree, we have V at P equal to minus 1 by 4 pi epsilon naught P by R square. Now come to equipotential surface. A surface of which every point is at the same potential is called an equipotential surface. An equipotential surface may be either hypothetical or real. Example of a hypothetical equipotential surface. The electric potential at a point P due to a point charge Q is 1 by 4 pi epsilon naught Q by R. The potential at the point P, that is Vp, will not change as long as R remains constant. Therefore, any hypothetical spherical surface centered at the point charge will be an equipotential surface, as shown in the diagram. Here, the spherical surfaces are equipotentials in presence of a point charge at their common center. Example of a real equipotential surface. The surface of a charged conductor is an equipotential surface. In fact, all points interior to a charged conductor have the same potential as that of a point on its surface. From that point of view, a charged conductor is an equipotential space bounded by its surface. We'll revisit this topic in the lesson Electrostatics of Conductors. Electric field and equipotential surface. Work done by an external force in transferring a charge Q naught from one point to another in an electric field is given by W equal to minus Q naught integration A to B E dot dl. This is equation 1, where the test charge has been moved from A to B by an external force without giving it an acceleration. Other symbols are standard. The work done is also given by W equal to Q naught multiplied by, within bracket, V at B minus V at A, bracket close. This is equation 2. Here, V at B and V at A denote the potentials at B and A respectively. Equating equations 1 and 2, we have minus integration A to B E dot dl equal to VB minus VA. That is equation 3. Now suppose the points A and B lie on an equipotential surface and the displacement of the tetras is also over the same surface. Then V at B is equal to V at A. And so we have integration A to B E dot dl equal to 0. This is equation 4. Therefore, E dot dl is equal to 0, or E dl cos theta equal to 0. Here theta is the angle between the electric field E and the displacement dl. The electric field as well as the displacement simply cannot vanish on account of physical realities. That is, on account of physical grounds. Therefore, cos theta equal to 0, or theta equal to pi by 2 radian or 90 degree. Therefore, the electric field is always normal to an equipotential surface. Let us consider the electric field due to a point charge and the associated equipotential surfaces. The field directions are radial and normal to the concentric spherical equipotential surfaces, as shown in the figure. For a uniform electric field, the equipotential surfaces will be plane surfaces normal to the field direction. A uniform field has been represented with equispaced parallel field lines in this diagram. Thus, if we are given the equipotential surfaces in a particular electric field, we can obtain the directions of the field at various locations. On the other hand, if we know the direction of the field at various locations, we can, in principle, draw the equipotential surfaces. The two statements above indicate a qualitative relationship between electric field and potential. But we are interested in obtaining a quantitative relation between these two. We have learned that the electric potential at a point is integration infinity to P F external dot dl equal to minus integration infinity to P E dot dl, where Vp is the potential at the point P, F external equal to minus E is the external force, E being the electric field, dl is an element of displacement. This equation gives the potential in terms of electric field. Typically, potential is easier to handle than electric field on account of its scalar character. Usually, it is sensible to obtain the potential in a given situation and then derive the field therefrom, and not the other way around. Therefore, we are interested in a relation that expresses electric field in terms of potential. Relation between electric field and potential. We are interested in a relation that will give us electric field if potential V is known. Let us consider two neighboring points in an electric field. For simplicity, let the points be situated on a field line. B and A are situated at a distance x and x plus delta x, respectively, from the origin. The separation distance delta x is sufficiently small so that the electric field between them is constant and is equal to E, while the potential at B and A are respectively V and V plus delta V. The potential difference between A and B is therefore V at B minus V at A equal to V minus, within bracket, V plus delta V, finally equal to minus delta V. It is equation 1. The work done in transferring a unit positive charge from A to B by an external force, which is equal and opposite to E, is force into distance equal to E into delta x. This is equation 2. Combining equations 1 and 2, we have E into delta x equal to V at B minus V at A equal to minus delta V. This is equation 3. Or E equal to minus delta V divided by delta x. This is equation 4. In the limit, E is equal to minus dV dx, equation 5. The quantity dV dx is called the gradient of potential. Note, the full form of the above relation in Cartesian coordinates is wherein we have considered the components of E and also the partial derivatives of the potential function P. This is, however, a relation not relevant too much for class 12. You'll be requiring it only in higher classes. Remarks. Please do not think too much about the negative sign in the equation E equal to minus dV dx. The negative sign has come from the equation V at P equal to minus integration infinity to P E dot dl, and is just a matter of tradition. We have seen that Coulomb's law provides a means for finding E, but the integrals involved are usually unmanageable. Gauss's law provides an alternative, but only for the symmetric such distributions. It is remarkable that the two-step process of finding the potential first and then derive the field from it is usually an easier option. Potential energy of a point charge in an electric field. Suppose the electric potential at a point P is Vp. By definition, Vp is the amount of work done in bringing a unit positive charge from infinity to that point by an external force without causing an acceleration in it. Therefore, to bring a point charge q from infinity to the same point by a similar process, the work required will be W equal to Q into V at P. Work energy equivalence tells us that W will get stored as the potential energy of the point charge Q in the field. We have also learned that potential difference VB minus VA is the amount of work done in bringing a unit positive charge from A to B by an external force without causing an acceleration in it. Therefore, work done when a point charge Q is transferred from A to B by a similar process is W equal to Q into, within bracket, VB minus VA, bracket close. W will get stored as the potential energy of the point charge Q in the field. In the event of the point charge returning to infinity, the stored energy will be released in form of kinetic energy of the charge. The kinetic energy gained by the point charge, if it returns to infinity from P, is therefore equal to E subscript K equal to QV at P. Similarly, if the point charge returns from A to B, it will gain an amount of kinetic energy, E subscript K equal to Q into, within bracket, V at B minus V at A, bracket close. Regarding the asterisks, gaining kinetic energy means undergoing acceleration. Electron volt, in short, EV. If an electron undergoes an acceleration across a potential difference of 1 volt, then the kinetic energy gained by it will be E subscript K equal to E into 1 equal to 1.6 into 10 to the power minus 19 joule. Here, E equal to magnitude of charge of an electron equal to 1.6 into 10 to the power minus 19 coulomb. This much of energy is a small but convenient unit of energy and is defined as 1 electron volt, in short, EV. Now, potential energy of a system of point charges. Let us assemble a collection of point charges by bringing them one by one from far away places. The first charge Q1 will not involve any work as there is no incumbent field. But the second charge Q2 will entail an amount of work equal to W2 equal to Q2 into V1 at P2, where V1 is the potential due to Q1 and P2 is the location of Q2. That is, W2 is equal to 1 by 4 pi epsilon naught Q2 into Q1 divided by R12, where R12 is the distance between Q1 and Q2 when they are in position. Now we bring in Q3. Work done will be W3 equal to Q3 into V12 at P3, where V12 at P3 is the potential due to Q1 and Q2 at P3, the location of Q3. Thus, W3 is equal to 1 by 4 pi epsilon naught Q3 within bracket Q1 by R13 plus Q2 by R23, where R13 and R23 are the distances between Q1 and Q3 and Q2 and Q3 respectively when they are in position. Similarly, work done to bring in Q4 is as given in the equation. I will not read it out. Therefore, the total work done in assembling the first 4 charges is it's a long expression. I will not read it out. So, an assembly of n point charges will involve an amount of work This is rather a concise expression. Amount of work W is equal to 1 by 4 pi epsilon naught, sum over I equal to 1 to n, and again a sum over j equal to 1 to n, where j is greater than I, qi qj divided by rij. Here the condition j greater than I avoids counting the same pair twice. The work done in the process will remain stored as the potential energy of the assembly of the point charges. On dismantling the system, the same amount of energy will be liberated. Potential energy of a system of 2 point charges in an external electric field. Following the threads of earlier discussions, we compute the work done in placing 2 point charges in an external electric field as W equal to W subscript field plus W subscript mutual, where W subscript field means work done in bringing the point charges to their positions in the field, and W subscript mutual means work done in the process against each other's influence. Now, W subscript field is equal to Q1 multiplied by V at P1 plus Q2 multiplied by V at P2, where V at P denotes potential and P1 and P2 are the locations of the point charges Q1 and Q2 in the field, and W subscript mutual is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12, where R12 is the separation between the charges when they are in positions. Therefore, total work involved W equal to Q1 V at P1 plus Q2 into V at P2 plus 1 by 4 pi epsilon naught within bracket Q1 Q2 divided by R12. Work energy equivalence tells us that W will get stored as the potential energy of the point charges in the field. Now, potential energy of a dipole in a uniform electric field. Let us consider an electric dipole in a uniform electric field. All parameters have been illustrated in the figure itself. We have learned earlier that a dipole experiences a torque in the electric field. The torque tau is P cross E, where P is the dipole moment of the dipole and E is the electric field. Suppose an external torque, which is equal and opposite to tau, rotates the dipole from an initial angle theta naught to a final angle theta without causing any angular acceleration to the dipole. Work done in the process is W equal to integration theta naught to theta tau subscript ext d theta, which is equal to integration theta naught to theta tau d theta, because the electric torque tau is equal to external torque tau subscript ext. Then substituting for tau, we have integration theta naught to theta Pe sin theta d theta. We carry out the integration and insert the limits. We get minus Pe within bracket cos theta minus cos theta naught. Let us select theta naught equal to pi by 2 as the reference point. At this orientation, that is at this reference point, the dipole will be in an equipotential surface where it will have zero potential energy. That is QV plus within bracket minus QV equal to 0. Then W equal to minus Pe cos theta can be expressed as minus dot product of vectors P and E, that is P dot E. The work done will get stored as the potential energy of the dipole in the electric field. So the dipole potential energy in an uniform electric field is minus P dot E. This brings us to the end of the lesson 2 of chapter 2. We'll consider electrostatics of conductors, etc. in the next lesson. Till then, goodbye and thank you for watching.